The time is exactly 3:08 p.m. The digital thermometer outside a luxury boutique reads 49.7 degrees Celsius. It ticks to 49.8, then 49.9. Finally, it settles on a perfect 50.0 degrees Celsius. Look at the skyline. The Burj Khalifa is not melting. The Dubai Mall is not plunging into darkness. A colossal Emirates passenger jet is still idling on the shimmering runway. Everything appears absolutely normal. But if nothing is collapsing, why has every major mechanical system in the city suddenly spiked its power demand at the exact same second? What you are witnessing is not a reported crisis in downtown Dubai. We are initiating a technical stress test simulation based on extreme regional data. If every single luxury hotel desperately requires more cooling power right now, which location is quietly allowed to warm up first? If you want to know what this city is secretly sacrificing to survive this afternoon, we have to go back to a time when the sun was not even in the sky. The time is 5:12 a.m. The city is draped in absolute darkness. The vast corridors of the mega malls are empty. The luxury restaurants, which usually define the elite hospitality sector, have not yet fired up their commercial kitchens. The endless fields of glass facades have not yet received the full punishing radiation of the desert sun. Deep underground industrial water pumps are quietly pushing millions of gallons of freezing water through a sprawling hidden network. During our technical stress test, this pre-dawn quiet is the most critical window of the entire day. It is the time when the mechanical systems can build a vital margin of safety. Dozens of the most iconic structures in the urban core do not rely on their own independent climate systems. They drink from a massive shared district cooling network. Records show this network provides hundreds of thousands of refrigeration tons of contracted capacity through interconnected plants. This hidden river of cold serves the tallest towers and the grandest fountains. Are these famous landmarks truly independent architectural triumphs, or are they simply different organs feeding off the exact same mechanical bloodstream? If the breathtaking skyline completely depends on a labyrinth of underground pipes that tourists never see what is actually the most important structure in the city? Are the engineers merely storing cold water right now, or are they desperately buying a few extra minutes of survival before human demand inevitably catches up with mechanical supply? The most dangerous moment of an extreme heat wave is not when the thermometer peaks. It is the quiet moment when the system still has the capacity to prepare. But the first thing to shatter the artificial 26-degree barrier between human comfort and desert reality is not the rising sun. It is something as simple as a glass door. The time is 9:47 a.m. A sleek automatic door glides open at the entrance of a high-end commercial plaza. For 3 seconds, a thick wave of 50-degree air rushes into the meticulously cooled lobby. A chilled water coil hidden in the ceiling instantly detects the intrusion. It absorbs the thermal energy. The cold water inside the pipe absorbs that heat and carries it away from the building, rushing back to a central plant to be chilled once again. The system must violently strip both the heat and the suffocating humidity from the air before anyone notices. Dubai does not magically create cold air. It operates as a giant, relentless machine that constantly moves heat away from where humans are standing. Is an automatic sliding door a welcoming entrance, or is it a gaping hole in the city climate defense shield? Is the real enemy the physical heat you feel on your skin, or the invisible water vapor that sneaks in alongside it? When you step from a blistering 50-degree street into a crisp 24-degree lobby and call it luxury, how many industrial pumps had to quietly accelerate just to maintain your illusion? Let us look at a subtle engineering reality. Authorities have previously suggested that raising the thermostat by just 1 degree might reduce cooling energy consumption by roughly 5%. If raising the temperature by a single degree can massively reduce the strain on the grid, why would any operator wait until a total blackout to take action? Could the very first sacrifice of the day be completely invisible to the naked eye? Is a 5-star hotel suite still considered the pinnacle of luxury if the management secretly lets the temperature drift from 24 degrees to 25 degrees? A single room increasing by 1 degree means almost nothing. But what happens when hundreds of thousands of rooms send the exact same desperate demand to the power grid in the exact same hour. The time is 12:36 p.m. The heat wave has fully gripped the city. Millions of residential air conditioners are roaring. Hotel suites are fully booked. The commercial centers are packed with tens of thousands of visitors seeking refuge. We must consider the economic dynamics of the luxury dining and hospitality industry operating at this exact moment. Premium restaurants face towering operational costs just to keep their dining rooms hospitable. Their commercial kitchens generate massive internal heat, while peak foot traffic trends push their air handling units to the absolute maximum. Elevators are in constant motion. Heavy water pumps are screaming at maximum revolutions per minute. The district cooling plants are devouring electricity. The graph in the central dispatch room shows the electrical load climbing a steep, terrifying mountain. The true enemy today is not one specific machine consuming too much power. The true enemy is every single machine in the city demanding maximum power in the exact same hour. We must look at the staggering scale of this operation. In 2025, the city produced 62.21 terawatt-hours of electricity. The peak demand reached a massive 11.39 gigawatts. The total installed generation capacity by the end of that year was nearly 18,000 megawatts. Is the most terrifying threat a lack of raw electricity, or is it the sheer logistical nightmare of delivering that power to millions of different endpoints simultaneously? A massive total capacity sounds like an impenetrable fortress of energy, but is every single megawatt truly available to be deployed in a fraction of a second? How much excess infrastructure should a desert city build and maintain just to survive the few most brutal days of the year? Is that unused excess capacity a terrible waste of capital, or is it the necessary price of a promise that wealthy tourists will never have to sweat? Do not be mistaken. A temperature of 50 degrees does not automatically crash the power grid. The city might have plenty of electricity, but what happens if it simply runs out of cold water exactly where it needs it most? The time is 3:08 p.m. We are back at the peak of the mountain. The thermometer reads 50.0 degrees. Look closely at the sprawling district cooling network beneath the urban core. The total volume of freezing water is dividing into multiple branches. One branch heads to the residential districts, another to the luxury hotels, and a massive flow directs itself toward the Burj Khalifa and the major shopping centers. Suddenly, a localized sector on the digital control map blinks with a warning. For just a few minutes, the total cooling demand in this specific square kilometer is mathematically exceeding the volume of chilled water that the pipes can deliver. The system must initiate the sacrifice matrix. Let us look at the tallest building on Earth. The Burj Khalifa has a reported peak electrical demand of roughly 36 megawatts. It consumes an average of about 946,000 liters of water every single day. It relies on 57 elevators, 7 massive double-story mechanical floors housing substations and pumps, and pressurized air-conditioned refuge areas located every 25 floors. Does the Burj Khalifa represent humanity conquering the desert, or did engineers merely build a mechanical system large enough to temporarily hold the desert at the front door? How much is a multi-million-dollar view from the 100th floor actually worth if your floor is selected to be the first one to lose its cooling priority? If a mechanical room high in the sky loses its thermal safety margin, do you really believe the heat will politely stay contained inside that room? Is the most impressive thing about the Burj Khalifa its breathtaking height, or the thousands of hidden screaming machines that prevent the people inside from suffocating in the heat? Here is the simulation. You are sitting at the central command console. You have a finite amount of thermal defense remaining for this hour. Do you choose to make 10,000 shoppers in the mall slightly uncomfortable by raising the temperature by 2 degrees, or do you risk an overheating failure in a critical electrical substation? Is raising the temperature in a luxury shopping center a catastrophic failure, or is it a brilliant tactical maneuver to prevent a total blackout? Would you turn off the spectacular facade lighting of the Burj Khalifa first, or would you restrict the air conditioning in a premium hotel lobby? Must the Dubai fountain continue its magnificent water dance if the pumping power it requires could be used to stabilize the grid? Will you protect the systems that maintain human life, or the systems that maintain the flawless global image of the city. If a corridor gets slightly warmer, there is no panic. There are no alarms. People just start walking a little faster. A tourist wipes their forehead. A luxury boutique suddenly feels empty. But then a visitor pulls out their phone and records a video complaining about the uncomfortable heat. This city sells perfection. When perfection breaks, the economic model shudders. The risk of losing that pristine reputation hangs in the air. You must ask yourself if pushing these boundaries makes the risk still worth it. An engineered ecosystem like this does not need to physically explode to fail. It only fails when it allows the paying customers to physically feel the climate they paid a fortune to escape. But chilled water is not the only fluid under immense pressure right now. This city still has to pump nearly 500 million gallons of drinking water before the day is over. The time is 4:21 p.m. The chilled water running through the closed-loop pipes under the city center is not the exact same water that flows out of a golden faucet in a luxury resort. So why does a 50-degree afternoon push both of these distinct systems into the exact same survival scenario? They collide because they both demand enormous amounts of electricity, relentless pumping power, and flawless continuous operation. In 2025, the peak daily demand for desalinated water hit 487 million imperial gallons. That is roughly 2.21 billion liters in a single day. The installed desalination capacity at the end of that year was listed at 495 million imperial gallons per day. You might look at those numbers and do a simple mathematical subtraction. Does that narrow gap mean the city is hovering just 8 million gallons away from a catastrophic drought? No. That basic subtraction is a trap. It does not account for the reality of operational schedules, massive strategic reservoirs, buffer tanks, and the complex geometry of the distribution network. There is no immediate shortage of water. But if the numbers do not prove an immediate crisis, do they prove the terrifying, relentless scale of the machine that must operate perfectly every single day? If the system experienced a sudden, unexpected strain, would you cut the water supply to the lush landscaping of a golf course before you restricted the flow to a hotel swimming pool? Should the magnificent Dubai fountain be completely drained and shut down before local residents are asked to consume less water? Can a luxury resort on the Palm Jumeirah still sell the image of a tropical paradise if its pristine pools and rain showers are suddenly subjected to a strict resource priority matrix? Does extreme luxury in Dubai begin with a polite greeting at the hotel reception desk, or does it actually begin deep inside a brutal industrial plant boiling the salt out of ocean water? Is a desert civilization that consumes over 2 billion liters of artificial water on a peak day truly controlling the forces of nature, or is it simply spending billions of dollars to endlessly rent extra time from nature? A 50-degree day does not dry up the reservoirs. It simply forces the power grid, the water pumps, and the cooling networks to march together into their most punishing operational hour of the year. The hotels can raise their thermostats. The fountains can be paused. The lawns can go thirsty. But there is one massive economic engine in this city that cannot hide in the shade. It must do business directly with the 50-degree air itself. The time is 5:37 p.m. An Emirates passenger jet, a marvel of modern aviation, sits at the end of the runway at Dubai International Airport. The intense heat rising from the tarmac violently distorts the visual field. The atmosphere around the massive wings is physically changing. Aviation experts know that high temperatures drastically increase the density altitude. The air becomes significantly less dense, meaning there are fewer air molecules flowing through the heavy engines and over the wings. This physical reality means engine thrust is inherently reduced. The aircraft requires a much longer runway to generate lift. Its ability to climb quickly into the sky is compromised. Essential performance calculations must be entirely rewritten. The severity of this issue depends heavily on the specific aircraft, its payload, the runway length, and manufacturer data. The planes can absolutely still fly. But if the critical safety margins shrink, what must be removed from the equation first? The commercial cargo, the heavy jet fuel, or the paying passengers? In 2025, this global transit hub handled 95.2 million passengers, connecting 291 destinations across 110 countries, via 108 international airlines. Let us simulate a long-haul flight that suddenly finds its takeoff performance margin too narrow for the 50-degree air. Would you rather the airline quietly offload your luggage to save weight, or would you prefer the captain to keep you sitting on the runway until the temperature finally drops? Is a 1-hour delay on the ground in Dubai simply a local inconvenience, or is it a localized virus that immediately infects thousands of connecting flight schedules across the entire planet? A single passenger missing a connection is a personal frustration, but what happens when an airport processing 95.2 million people starts cascading those tiny deviations across a global network? This city built its immense wealth by selling its perfect geographic location between east and west. But how valuable is that location if the hottest hours of the day become the most operationally restrictive hours for heavy aviation? Can a global transit hub continue its aggressive economic expansion if its vital operational margins are slowly being eaten away degree by the desert air? The domino effect is brutal. High heat causes a drop in air density. That alters a performance calculation. A flight is delayed, passengers miss their connections, flight crews time out. For the first time all day, 50 degrees in Dubai is no longer just a problem for Dubai. It is now flashing red on departure screens thousands of kilometers away. The sun finally begins to dip below the horizon. The glaring light fades. The air temperature slowly starts to drop. It feels like the most dangerous moment has passed. But who told you that a setting sun means the mechanical pressure disappears? The time is 8:16 p.m. The city is illuminated in a vast sea of neon and architectural lights. The streets are suddenly crowded. Tourists pour out of their rooms and flood into the restaurants and promenades, drastically shifting the foot traffic trends toward the entertainment districts. The temperature has officially dropped from 50 to 41 degrees. Do you think 41 degrees at night is a relief, simply because the number is lower? Look closely at the coastal environment. The sun is gone, but a thick, suffocating blanket of humidity is rolling in from the Arabian Gulf. Furthermore, millions of tons of steel, glass, and concrete have been baking in the sun all day long. They are now radiating that stored thermal energy back into the night air. Inside the megastructures, the cooling demand remains brutally high. The air conditioning systems are no longer just fighting the ambient heat. They are fighting the crushing humidity and the concentrated body heat of hundreds of thousands of active people dining and shopping. The sun has vanished, but how much violent solar energy is still trapped inside the bones of the city architecture? Does cooler but heavily moisture-laden air actually give the industrial chillers a chance to rest? Is the most dangerous enemy the high number printed on a weather application, or the heavy invisible water vapor that must be mechanically dragged out of the indoor atmosphere? Why does this city experience its peak human activity at the exact moment its machines have just survived hours of maximum stress? If the daytime is dedicated to fighting pure heat, and the nighttime is dedicated to fighting severe humidity, at what hour does the infrastructure actually get to recover? During the day, Dubai fights a war against visible heat. At night, it fights a quiet, desperate war against the water suspended in the air. If this extreme pressure extends deep into the night, why does the city not collapse into chaos every single summer? The time is 11:43 p.m. We must strip away the cinematic drama and look at the brutal truth of mechanical engineering. The city does not collapse. Dubai survives because of profound overlapping layers of defense. The first layer is the sheer scale of power generation. The installed capacity is vast, built deliberately to absorb extreme economic and environmental shocks. The second layer is the interconnected nature of the cooling network. The downtown core is not gambling its survival on one single chiller plant. The third layer is spatial zoning, allowing a local mechanical issue to be isolated before it spreads. The fourth layer is thermal inertia. The millions of tons of concrete and millions of gallons of water inside these buildings do not heat up instantly. They absorb the shock, giving human operators precious time to react. The fifth layer is the art of micro-adjustments. Operators can slightly raise set points, delay non-essential pumping, and shift loads without the public ever knowing. The final layer is the invisible web of sensors that detect a failing margin long before a tourist feels a single drop of sweat. Is a massive reserve capacity a waste of capital, or is it the only barrier standing between a silent computer warning and a humiliating global news headline? Why must a city spend billions on heavy machinery that is only considered successful when absolutely nobody notices it exists? Is a perfect engineering system one that never experiences stress, or is it one that is designed to quietly sacrifice its own perfection before it sacrifices human safety? Does this city actually defeat the climate, or does it simply detect its own failures fast enough to patch the armor before the climate wins? If the city has to secretly dim the lights and warm up a hallway just to survive the night, is that an operational failure, or is it the ultimate definition of resilience? The answer is clear. 50 degrees is not a kill switch. It is the ultimate auditor. It is the number that forces every single hidden layer of defense to step out of the shadows and prove its worth. After 24 grueling hours, the skyline remains untouched. So did the extreme temperature actually destroy anything at all? The time is 4:58 a.m. A new day is breaking. The Burj Khalifa still pierces the sky. The major shopping centers are preparing to open their doors. Heavy passenger jets are descending onto the runways. The drinking water flows cleanly from the taps. The industrial pumps deep underground are still spinning, preparing for another brutal cycle. The city survived, but it did not survive because 50 degrees is a harmless number. It survived because every single fraction of a degree was violently pushed back by billions of dollars of infrastructure, relentless mechanical power, aggressive maintenance, and cold, calculated operational sacrifices. Is an extreme heat wave harmless, or did the city only survive because 1,000 silent machines absorbed the trauma before you could feel it? Is Dubai a city built in the middle of a desert, or is it actually a colossal industrial engine that never stops pushing the desert away? Does the concept of extreme luxury still feel glamorous if you are forced to look at the massive screaming machinery required to sustain it? If you were sitting in the control room during the most dangerous hour of the day, what would you choose to sacrifice first? The dancing fountains, the architectural lighting, the temperature of the shopping mall, the hotel, swimming pools, or a slot in the international flight schedule? While this entire 24-hour stress test was a hypothetical simulation, the engineering reality behind it is absolute. Dubai does not defeat the climate. It transforms the climate into an industrial process that must be managed without a single second of hesitation. And perhaps the only thing that was truly destroyed during our simulated 24 hours at 50 degrees was the fragile illusion that the crisp, cool air in the desert was ever natural to begin with. What would you have sacrificed to keep the city alive? Let me know in the comments below, and subscribe to the channel for more deep dives into the machines that run our world.